Okay, Hubert, you've got 12 minutes. I'll make noises before the end of your talk. Okay, go ahead.
Hi, everyone. So I'm Hubert Bretonnière. I'm a third-year PhD student at the IIS and APC in Paris. And today we'll talk about one thing we've done for Euclid, the astronomical survey from the ESA, and one other thing we're doing right now, and it's currently in progress, which are a simulation of galaxies. Oh, yeah. Sorry. Simulation of galaxies and also segmentation of galaxies, so two different projects. So I'm talking for my project, but we are also a big team with, for example, Alexandre Boucaud, Marc Lorta's company, and François Lanusse, and collaborators. So first, what we've done is to use a deep learning algorithm to simulate realistic galaxies, or at least more realistic galaxies than classical analytical profiles. And I will tell you a bit about that and how we applied that, and a bit of discussion about the velocity, the speed of simulation, and what to think when you develop an astronomical pipeline if you want to use machine learning. So I will not go into too much detail for the architecture, but just the idea is to use a variational autoencoder. That is a model that takes into input images, for our case galaxies, realistic images from the Hubble Space Telescope, and learn a distribution of this image into a latent space thanks to convolutional neural networks. And then sample from this distribution, and thanks to also another convolutional networks, it decode the information and reconstruct the galaxy. In our case, we have also the interesting thing that our simulation are noiseless and deconvolved by the PSF, and it's also always interesting to put some physics, because we are able to deconvolve by the PSF because we know the physics of the Hubble Space Telescope PSF, and so we put some physics on our model. So this is good, but the problem is that you can generate quite random galaxies, but you don't have a really, you can't simulate a precise galaxy with some physical parameters. So what we've done is to use also a regressive flow that learns how to map your catalog. So for example, your physical parameters, morphological parameters, to know where to sample into your encoded space of your variational autoencoder, to then decode it and produce the galaxy that have the morphological parameter you put into the input of your VAE. So this is some result of our algorithm. So you can see we can create some complex galaxies with spiral arms. This thing is not working so well. Spiral arms, rings, clumps, and things like that, which are really more complex than the analytical. Okay. The analytical simulation we have currently in the Euclid pipeline. We also have a control on the shapes. As you can see here, we've created galaxies with increasing, decreasing ellipticity and increasing size, and the galaxy produced are indeed following the good trend. We use that in our paper for Euclid that forecasts the number of galaxies that Euclid will be able to resolve with interesting morphology, to have a forecast on the possibility for galaxy science for Euclid, so more the legacy part of Euclid. This is a plot that I wanted to precisely highlight for this conference on the potential of machine learning, because this is the a benchmark we did where we look at the speed of our algorithm compared to the actual algorithm that create the galaxies for Euclid. So our galaxies are a bit more, largely more complex and realistic, but this is slower. But what is interesting here in this plot, where we have the how much slower is our algorithm compared to the classical one, and here the number of galaxies we're simulating, and we have three different information in this plot. Is that the square are this galaxy simulated with CPUs, and the stars are when we use our model with GPUs. And so you can see that with GPU, you're always faster. This is something new, but it's interesting to see that if you want to use that in a pipeline for astronomical survey where you want to simulate a huge number of galaxies, well, try to have GPUs in your pipeline. And the other thing is that the difference of colors is when you use different batch size. So your algorithm is made naturally to create your galaxy in parallel. And so if you want to, so you're always faster. So when you have a darker color, it means that you are producing galaxies in parallel. And so it goes really faster when you use a different batch size. And so this is also a thing you need to think when you are creating your pipeline, because, for example, in Euclid for now, the pipeline is made so one galaxy is produced at a time. And so we can't really use batch in the simulation. And so this is a big bottleneck for using deep learning in the current Euclid pipeline. So yeah, it was a bit fast, but this is what we've done with simulation. Now I'm going to talk about the second application we're doing with the probabilistic segmentation of blended galaxies. So just a few words about blending. So blending is when you observe your sky with your telescope, and you can have two galaxies that are physically separated, meaning that they are in the same line of sight, but in two different redshift planes, for example. But when you take your picture, well, the two galaxies are projected on the focal plane, and they look like they are mixing, even if they are not. And so when you're doing shape measurement, even more when you are interested in shear, if you don't recognize those galaxies as two different galaxies, you introduce big biases in your shear measurement, and it's really problematic for missions like Euclid. A good way to identify this zone, this blending, this overlapped region, is to take what we call segmentation maps, where you take your galaxy and you transform your galaxy into a binary map where black is background and white is the galaxy. And so when you have an overlapping region, you can see it clearly. And so the goal of our algorithm is to take this into input and to create those kind of maps where you detect the galaxies and you also detect the blending zones. Here again, I will not go too much into the detail, but it comes from an article of Simon Cold and al. That use that for medical imaging. And what is interesting just to know is that you have a classical part with a UNet which creates segmentation maps, but we also learn a distribution of our maps so that during inference you can sample many times from your distribution that you've learned, and you can concatenate that with your segmentation map created by your UNet, and you will create different segmentation. So every time you sample from this distribution, it will create a slightly different segmentation. And so what you can do with that is to take, for example, the mean and the dispersion of your segmentation, and it will tells you where your model is sure of what it's producing or where it has uncertainty. So for example, here where you have this image where there is like this hard zone where there are three galaxies that are overlapping, when you do your segmentation, you can see that he knows that there's a blend here, but he's producing a strange pattern here. But you see that when you look at the dispersion of all your prediction, he knows that what he's producing here is not sure because your dispersion is big. And so it's good because you can take the mean and give the people that are going to analyze, for example, to do shear measurements. You can say, okay, here you have a blended region, but be careful because we are not totally sure of what we are producing, which is really interesting when you are doing science. This is another example where we start to see that we have interesting behavior of our uncertainty prediction. That, for example, here you have this also these blended galaxies that by eyes you can't even see the second galaxy that is here. This is our prediction, our average prediction. So you can see that we can find the blended region, but the dispersion is really big inside the blending region that is hard to find, and quite zero on the other parts that are easy to find. And here it's another example to see the interesting behavior of the dispersion is that the dispersion is higher on the frontier borders of your galaxy where your flux is really low. And so, of course, it's hard to predict where the galaxy really ends, and our model is able to capture that. So two results that are preliminary but are really, really encouraging is that for the metrics, just don't look at the dispersion of your metrics, but just the capacity of identifying isolated galaxies or blended galaxies. We have like close to 100% of completeness and purity for isolated galaxies up to magnitude 25.2, which is quite great. And even for blended galaxy, we already have a great result. So I think it's really promising, even compared to state-of-the-art classical deblending algorithm like Sersic or something like that. Another thing that is interesting is to look at the mean variance of our prediction regarding the magnitude of the galaxies. And here again, you can see that the uncertainty increase with the magnitude, which is something physically that is completely, we want that. Like, I mean, it's physically motivated that your prediction is more uncertain when you have fainter objects. And so this is something that we find in our model, and which is interesting to see that we didn't put any physical information in, but just the raw images, and the uncertainty follows something that is physical. So yeah, this is still in continuation, but we have already great results for the identification, and even the uncertainty starts to make sense, and we are currently analyzing really how to understand what is going on, but it's very interesting to see that there is already physics in the uncertainty. So yeah, thanks for your attention. And this is, for example, a field that we created. This is completely machine learning, deep learning simulated.
Thanks, Hubert. So we have some questions on the Slack, in fact. So a question from Angus Wright. Very interesting talk. Dumb question. Is there a criteria you can use to determine whether your encoder-decoder galaxies are as realistic as directly injected real galaxies observed in deep imaging, i.e. that the simulated galaxies are sufficiently complex for arbitrary science?
Yes. So this is a good question because, yeah, the metrics to see how realistic is quite hard. You can find some metrics, and François did that in his paper, on the first paper where he developed the code, is to look at the morphological parameters like the asymmetry, the smoothness, and things like that. And he showed that the model was indeed reproducing the distribution of those morphological parameters. So, yeah.
Okay, and then there's another, yeah, it's sort of like the same question. How do you check that generated galaxies are physically sound and the statistical distribution of properties in a big sample reflects real observations? Yeah,
so we've done that. I didn't, but François did that for the morphological parameters, and we did that with the, we checked for the radius, the radius, the ellipticity, and things like that, and we showed that we are following the same trends as analytical simulations.
Okay, and then there's one last, more technical question. How do you actually suppress the fuzziness in the output from the CNN so that you get defined structures in your simulated galaxies?
Can you repeat the question?
Yeah, I'm not sure if I understood. How do you suppress the fuzziness of the typical outputs from a CNN so you get these defined structures in your simulated galaxies?
Okay, I'm not sure to understand, but I think we can work on that with the size of the encoded distribution we have in our latent space. And there's many works that show that if you put a bigger dimension in your latent space, your distribution, your output will be fuzzier, and you can have more structures. And if you put a smaller dimension in your latent space, your galaxy will be completely round. I don't know if it answers the question.
Actually, it's related to that. What is the size of the latent space that you're using optimally?
For our variational autoencoder is 32.
Okay. And what's the exact role of the autoregressive flow that you're using?
Okay. So when you have only your variational autoencoder, what you have is in your latent space, you have the whole distribution of your data set. And the only thing you can do is to sample quite randomly from this latent space, and it will create a galaxy that is good, but you don't have control on the parameter of this galaxy. And what we do with a regressive flow is to map your input catalog, so you just have your physical parameters, and a Gaussian distribution, and it transforms this Gaussian distribution parameterized by your physical parameter to tell you where in your latent space you need to sample to produce a galaxy that has the physical parameters of your catalog.
So sorry, it's a mapping between the input catalog and latent space, right?
Yes.
So have you tried to interpret what your latent space is actually learning in this procedure? Because you have that mapping, right?
Yes. No, I didn't.
Okay.
It's interesting, yeah. But
yeah.
So what we think is that we can hope that our latent space is quite organized with the different galaxies in different spaces. And we can hope, yes, that this mapping is learning just where the galaxy with certain parameters are situated in the latent space. Yeah,
you want to know, whether you're asking the question, what is an object, essentially? So there's one last quick question at the back.
Yeah, have you tried to
propagate... I'm sorry, say your name first.
Gary Davidson.
Hi, Gary, I didn't recognize you.
Hi, Henry. Have you tried to propagate the uncertainties from your segmentation map into the photometry you extract, so magnitudes plus minus error bars, and especially compare that to the error bars that you may get with the classical approaches? Is a big deal.
Yeah, that's something we want to do. It's currently,
Okay.
It's definitely something we'll do in the paper.
Thanks very much again, Hubert. I'm afraid we'll have to go on because there's lots of other super interesting talks to listen to as well. Thank you again.